So in section 24.2, we're going to be focusing on volume. And so any real object takes up space. So we want to think of volume as the space that we're actually taking up. And so if we're looking at some object like a box, we mean the volume is actually, the space that it contains inside a container, so the capacity if we were to fill it up. Now, the actual box itself is made up of material, and the volume of that is not really what we're concerned about. We typically think of that as kind of like surface area. So we want to make sure we're looking at the distinctions between that. The volume is kind of what will fit inside of it. The material that makes it up, that's going to be more of the surface area. So let's go ahead and look again at our standard units here. And so our standard units here for volume is we could look at an actual cube. So something that is 1 unit long. And so we'll go 1 unit by 1 unit by 1 unit, and it'll create this kind of cube. A lot of times, again, in the metric system, we'll think about these as using a centimeter, or in our English system, using inches here. If each thing was 1 inch wide, we would think of this as a cubic inch. But we'll later talk about as just making a actual unit standard here. So this would be a 1 cubic unit if it was just 1 by 1 by 1. Cubic centimeters are nice. Again, with the metric system, a cubic centimeter is what we call 1 cc. And so that's just a box that is 1 centimeter by 1 centimeter by 1 centimeter. And 1 cc is nice because actually if we talk about the volume of how much liquid we could fill inside of a cubic centimeter, that's actually our definition of a milliliter. So you might see that in a doctor's office, they talk about cc's, which are exactly the same as milliliters. So how could we convert here? So how many cubic centimeters does it take to fill up a cubic decimeter here? Again, with the metric system, this makes it a lot nicer being able to convert from one into the other. So let's look at this first one here. How many cubic centimeters does it take to fill a cubic decimeter? So again, 1 decimeter is equal to 10 centimeters. So if we want something that's a decimeter, a cubic decimeter, that means that it is 10 centimeters by 10 centimeters. And then also it's going to be, since we're talking volume, it will also be 10 centimeters deep as well there. So 1 decimeter by 1 decimeter by 1 decimeter, that's what we talk about a cubic decimeter there. And so we're doing a lot of little centimeters within there. So how many will we actually have? Well, it would be 10 times 10 times 10. So 10 to the third power, or 1,000 cubic centimeters. Vice versa, we were going the other way. Conversely, 1 centimeter cubed, or 1 cubic centimeter, is what portion of a decimeter cubed? And it's 1/1000th of it, because it would just be one little square from that. And so when we start talking about different units, we're typically used to gallons and then quarts, cups. Again, the metric system is a lot nicer because those conversions actually coincide with one another there. But there's, if we were to use our metric to just do like a cubic meter, so 1 meter by 1 meter by 1 meter, that's a pretty large amount of volume or of material that would fit inside of it. So that's not too common. So this is why we like to use smaller units. And so we talked about how if we have 1 cubic centimeter, right, that equals to 1 milliliter. But that ends up being very small as well. So something that's a bit more practical would be kind of the figure that we had on the last slide here. If we had a cubic decimeter, so 1 decimeter, which again is 10 centimeters by 10 centimeters by 10 centimeters. That's what we call a liter. So a liter is how much we would have in a cubic decimeter. So the metric system offers a lot nicer relationships, and for practicality as well. We could kind of fine tune whatever size we want. If we're talking medication, those milliliters are nicer. If we're talking about fluids to perhaps drink or so, those liters end up being a lot nicer as well. And so let's look at this activity here. We want to figure out the volume, so the capacity right within it, and we're going to just use our standard cubic unit here. So no units, just kind of talking about it in terms of a cubic unit. So we have a skyscraper here. It tells us how many stories, and what's shown here is the just the first ground level. So we want to know what the volume is of the bottom story of each skyscraper. So this first one here is, we are looking at these actual units that we have here. And so we see that it's going to be 42 cubic units. And we can actually count them across, right? We did that. So 1, 2, 3, 4, 5, 6. And then we have 1, 2, 3, 4, 5, 6, 7. So 6 by 7, that's going to be 42 cubic units, or we could count each single one if we wanted to as well. But there's 42 cubic units in there. That's going to be at the bottom floor there. Similarly, for the other building, we could count those, and we're going to see there is 40 cubic units in this case because we have 10 by 4. And that's just looking at that bottom level. So 40 cubic units in this case. There we go. Okay. And so maybe we'll go ahead and we'll look at this second portion here. It wants to know what is the area of the floor in the bottom story of each skyscraper. So we want to actually look at now the area within there. And it's going to be the same since we're kind of just looking at this two-dimensional. We're just going to go ahead and see that it's 6 by 7 as well, because we're just trying to kind of look, and maybe we should really be looking at the ground floor here, really on the actual floor there, right? If we were to have kind of that walking distance there, of where we would be in the room. So our area would actually be the same. It would still just be 42 square unit or units squared in this case. And similarly for this as well, because we're trying to see the area of walking around, it would just be 4 by 10. So 1, 2, 3, 4. Actually 5 by 1, 2, 3, 4, 5, 6, 7, 8. 5 by 8. Sorry, that's where the 40 came from. I had said 4 by 10 earlier, but it's 5 by 8, which will give us that 40 units squared for the actual area. And then we could talk about which skyscraper has greater volume. And now these numbers might get a little bit larger, so the easier way arithmetically would be to talk about the volume on that floor and multiply by how many stories it actually has. And that'll give us total volume. And we could do the same thing similarly for the second building here as well. And if we actually just multiply those, we could actually see which one would end up being larger and do a direct comparison here. There we go. And so we'll be able to see that the first building has more volume. Now, another way of doing this is just kind of comparing. We see that this first building has 2 more cubic units per floor. But it is shorter, right? And this one here has less per floor, right? But it does have a little bit more. So this extra story here, this 31st story, right, is going to give us a whole nother group of 40. And so we're trying to see, is this extra 2 enough, right? So if we do those 2 extra ones for all of those stories there, well, 2 times 30 would give us kind of that 60 there. and versus here as well, right? We would only get that extra 40 for one of those stories there. So we could see that eventually, as we go higher and higher, that first one would end up being a little bit larger. We won't know exactly how, but we could just do a comparison because it's just asking which one has greater volume in this case. So that's another way of just trying to do a comparison with these. Let's look at discussion 7 here. So what is the volume of each of these polyhedras here? So we'll do one of these. So let's look at this first one. And what I want to think about this is volume is I'm going to break this up into pieces. So I'm going to kind of break this up as I'm stacking these different levels on there. And so for the first one, the volume here is just 1 by 1. If we go to that next layer, kind of like a cake layer here, I'm going to have 4 because it's 2 by 2. And I could keep doing this all the way through. The third one is going to be 3 by 3 piece there. And then we'll have a 4 by 4. So I could break it up into pieces and then go ahead and just add all of those up together. So if we add those 1, 4, 9, and 16, our total here would end up giving us 30, and we're talking cubic units again. So again, using our isometric paper or dot paper here and creating figures on that with that standard unit. We could similarly do the same thing for the next figure here, where I would break this up into that kind of top portion and then the bottom portion as well. And we could just break it up as 2 different rectangular prisms there, or right rectangular prisms. And so for the top one, we see it's a 2 by 3 by 3, which gives us 18, and then the bottom is a 5 by 5 by 4, which gives us 100. And so the total would be 18 cubic units. So this is nice, just having these more abstract shapes, but being able to kind of break them up, the same way we did that with lengths and surface areas. So how does volume relate when we start to use scale factors here? So when they're congruent, so if we have a scale factor, then if we're talking surface area, recall that it increased by k squared, right? Because it was area. If we're doing volume, then it's going to increase by the scale factor cubed. So that's how these congruent shapes will be related to. So we don't always have to draw the new figure. We could use those relationships. So looking at this kind of original cube here to this larger one, it has a scale factor of 3. So that means that the volume will increase by 3 cubed, or 27 times the original in this case. And if we count all these cubes in here, we'll see that there's actually 27 times as many. So let's try this out with this example here. And so they're saying hidden shapes here, and it's referring to the one discussion in 7. So I went ahead and just copied it here. So recall this shape here from discussion 7. It was 30 cubic units. And so there's another shape that is similar to it, but larger, with a scale factor of 6. Now again, I don't want to draw that. I'm going to use my relationships of scale factors. So in this case here, oh, and I'm sorry, let me back up here. We are first doing X, which is congruent shape. So we know that congruent shape is going to have the same volume because they're congruent in this case. So for X, it's going to be exactly the same. What I was referring to here is Y. So we have another one that has a hidden shape, which again, we don't want to draw this out, but this one has a scale factor of 6. And so that means our volume, that factor is going to go up by 6 cubed times the original volume. So 6 cubed times 30, which is 216 times as much. So the volume of this new figure that has a scale factor of 6 would end up being 6,480 cubic units. All right, let's look at this example now, looking at a large prism that is similar to a right rectangular prism here with side lengths of 2, 3 by 2. So let's go ahead and draw this out, our original figure here. And then we know that this is 2 by 3 by 2. And so the volume of this rectangular prism here is going to be 12 units in this case. So let's focus on the volume here first. Keep kind of working backwards. But since the scale factor is 2, then we know that the volume will increase by 2 cubed. So by a factor of 2 cubed. So 8 times as much as the original. So the volume of the larger, or our larger prism here is going to be 8 times 12, which is 96. Okay, now let's focus on the surface area. And so the surface area, let's look at the front, which is 2 by 2 of our front region here. But it also has a back, right? There's 2 sides there. So front and back is going to be 4 times 2. So that's going to give us 8. Okay, so 2 by 2. And then there's 2 sides, a front and a back. And let's do the same thing here for the right and the left sides. So that's going to be a 3 by 2, which is 6. And there's 2 sides, the right and left. And then similarly, we'll do that for the bottom and the top in this case. So the bottom is going to be a 2 by 3, and that's 6, and then there's 2 sides, so 6 times 2. So the total surface area, if we add all of these up here, 8, 12, and 12 would give us 32. Now that's the original figure. Now if we want to go to the larger one, since our scale factor is 2, then we know that the surface area will increase by 2 squared, or by a factor of 4. So 4 times the original surface area of 32 will give us 128 units in this case. So helpful to draw some of the figures, but eventually using some of these relationships will help simplify that as well. And here's just an explanation from the textbook, but I put this so you could actually see the figures here, so you can see the relationship of the actual objects. Okay, so takeaway here again is the scale factors. We don't want to kind of draw the new figures every single time. Initially, that's fine. But for these weird, or I should say more abstract shapes, it might be difficult to sketch. We want to use the surface area, that it's going to be the scale factor squared, and then volumes would be the scale factor cubed.